Hello, my name is Rahul Mangharam from the University of Pennsylvania, and I'm here to talk to you about our efforts in developing open autonomous vehicle algorithms and software for open electric vehicle platforms. This is part of our broader research agenda as part of the Mobility 21 Department of Transportation, National University Transportation Center between Penn and Carnegie Mellon. This is a 6-year long center of over $14 million focused on the future of technologies of moving people and goods efficiently. So if we look at the first generation of autonomous vehicles, we've seen that it is heavily reliant on brute forcing using HD maps and hand-coded rules. And this has caused it to struggle to adapt to new and to complex driving domains. And this struggle is really, because it has largely relied on expensive and complicated sensor stacks and integration with internal combustion engines of regular drive-by-wire cars that are available in the market today. And essentially, the issue has really been tried to resolved by putting a new sensor in place for each edge case that has been detected, rather than really focusing on the underlying intelligence. Now, companies are focusing more on end-to-end based navigation, which poses its own issues of risk and liability. So as we transition to autonomous vehicle 2.0, we see that there is a need for a complete array of solutions, from micromobility to public transport to ride hailing to delivery, and also in goods to persons and logistics centers and warehouses. And essentially here, the challenge is how do we rapidly iterate and adapt different vehicle hardware platforms to the software stacks, where you have unique set of sensor calibrations and settings and unique use cases. And how can we have a reusable core of software and hardware autonomy core that can translate across and specialize across these different use cases and platforms. And that's where our focus is really on developing the OpenAV driving intelligence stack for very standardized open electric vehicle platforms that are coming to the market or are in with newer players and newer consortiums. And we focus on developing an advanced level of software hardware adaptability and a reusable autonomy core across these different platforms. Well, this is not a new idea, but this is an idea whose time has come. So it's the right idea and it's the right time to actually focus on this. And the way we apply this is in a very unique manner, where we develop 1/10 scale platforms essentially, and where we can do this in a faster manner, a cheaper manner, and a safer manner, because these are scaled down platforms. But that translates in the similitude of perception, planning, and control to the full scale EV platform. And we are essentially focused on this rapid prototyping of and testing, and also the training of engineers to work on the autonomous driving stack of these platforms. So what we develop is we focus largely on 3 aspects: the behavioral planning, dynamic path planning, and safe and agile overtaking; dynamic control, that is focusing on behavioral control strategies, driving interaction and decision making; and then we focus on sensor integration and sensor fusion. You would see here that we do not necessarily focus on perception per se, as that is part of the sensor integration aspect, but the perception algorithms would really be now as part of the specialized core or built on the reference of this full AV software stack. And this is by focusing on the AV stack, we are now also really heavily collaborating with OpenEV platforms and make it compatible across these set of platforms using very standardized software. So what we develop is OpenAV algorithms on Autoware, with 110 scale platforms. We then deploy this software on OpenEV platforms. We test in Pittsburgh and Philadelphia, and we distribute across the world. Our testing facilities, for example, are like this 23-acre robotic experimental facility in Philadelphia that allows us to do all sorts of stress testing, parking, navigation, interaction with pedestrians, passengers, and so on. And we work on a partnership model where we want to make sure that whatever we are developing has a rapid transition and a path to getting to the market, from research to testing and prototype development to further on production down the line. And we do this by actually working closely, and we're part as a premium member of the Autoware Foundation, and which has over 36 members, paying members. They are highly sort of vested in the success of Autoware, which is the open autonomous vehicle stack for general autonomous driving platforms. And we also start to collaborate with the Foxconn's motivated MIH EV consortium for that is essentially an example of the OpenEV platform. However, we are agnostic to the specific EV platform, but we do have certain candidate platforms that we work with. As part of the F110 Autoware.Auto, we have well-formed deliverables, and our current focus is really solidifying the stack over here on with the deployments demonstrating dynamic path planning, obstacle overtaking, object detection, camera integration, sensor fusion, and interaction and decision making. Our collaboration model is that you sponsor the F110 Foundation, which is essentially this large team of people focusing on developing this AV stack for EV platforms. And you can also collaborate with us as part of this open source and open platform community. And so essentially with F110, we have developed a 110 scale platform for machine learning engineering on perception, planning, and control. It has a full-blown GPU on board, LiDARs, RGB, cameras, stereo cameras, and essentially mimics, an electric vehicle platform with autonomy capability. And it can drive at a speed of 50 miles per hour at this 110 scale. And we focused on really just getting together the platform from the mechanical aspect to the sensors to the overall AV stack, and have enabled a lot of research over the past 5 years in developing safe and coordinated autonomy. We focus largely on racing because that is really driving at the limits of performance. And that's really stress testing the entire system to make sure our algorithms are real time and also really fast. Essentially, our focus has been on how do we help the community build, code, and race, and really go from perception, that is, just using simple gap finding algorithms, to running SLAM on board. This is just demonstrating all the software that runs very smoothly on this platform in simulation and in hardware, going from different planning algorithms to such as RRT and search-based algorithms, all run very efficiently on this platform. And also advanced controls such as a hierarchical model predictive control, learning-based model predictive control for overtaking and navigating in complex and cluttered environments. And here's a demonstration of our cars actually using this actively in very aggressive and adversarial racing to demonstrate that the system actually works and now is translatable to the larger scale platforms. We have a large community of institutions of over 60 partners that basically use this platform, teach with this platform, do a lot of research with this platform. And this allowed us to now really have a way of training people also across these multiple domains, and viewing this as a system-wide problem. And this exposes, this level of complexity, but it still allows us to develop in a fast, cheap, and safe manner. Our team is widespread from University of Pennsylvania in Philadelphia to TU Munich, Oregon State, Clemson University, uh, University of Virginia, and University of Modena in Italy. So it's a very international team that contributes and develops this. Uh, our partners, even though they have autonomous Maseratis, they still use F110s for training and prototyping and testing all their algorithms first before they deploy it on large scale platforms. Our graduates are all in the top autonomous driving companies and universities. And essentially, this is something that over the years we have had several dozens of graduates who are in top positions now. So it's a great platform to teach and train and develop machine learning engineering skills for developing autonomous vehicles. We also host several competitions, and there have been 9 international autonomous racing competitions. The next one will be in October in 2021 as part of the IROS conference in Prague. In 2021, we have a whole fleet of production-ready platforms. We have a deep partnership with Autoware. The LG SVL simulator has F110 autonomous racing cars as part of their simulation platform now. It's fully integrated and available. We've had a host of dozens of research projects, hosted a ICRA 2021 workshop. And as I mentioned before, we will have this IROS F110 competition in October. So let's see what type of research has been enabled, so you get an idea of what kind of development we will be able to do as we move to the full-scale electric vehicle platforms. So we looked at, largely our research is focused on developing multi-agent strategies for autonomous driving, but using learning with improvisation. So we worked with that on model predictive control for racing, overtaking, and improvisation of how do you do balance safety and performance while not being too conservative, but still ensuring you're safe enough. We developed a fleet of different hardware platforms, and that are now having much more compatibility with OpenEV platforms. Look at multi-vehicle coordination and cooperation, different object detection strategies, multi-domain optimization, where the mechanical aspects, the planning aspects, the control aspects are optimized for the specific use cases, all automatically. Virtual racing front ends, where we have these virtual racing competitions worldwide, different types of visual SLAM, vision-based navigation, and indoor navigation systems, like where we can take the CAD of the blueprint of the business of the building model and convert that into a training environment for navigating through buildings. So here are a couple of themes of our research. So this one is on learning-based model predictive control, where we can actually automatically tune the driving behavior of a race car as we navigate through this track. So in the first instance, for example, we have a lap time of 20 seconds, and then we start to learn and drive more aggressively, but without crashing. A lap time then decreases to 15 seconds after several iterations. And here you can see the vehicle is even drifting. And this is automatically tuning the vehicle's planning and behavioral controller to learn from this racing routine over here. So this is to design the fastest car, but automatically learning the manner in how it can navigate this environment. We look at balancing safety and performance, because unlike civilian driving in racing, conservative but safe strategies are penalized. And so you want to figure out what is the maximum level of aggressiveness you can have while being safe enough. And so we do this in a multi-agent manner, and where we automatically can evaluate, how is the lead agent, what is the lead agent's driving policy, and based on evaluating that, we can learn their behavior and then synthesize, strategies to overtake them and beat them in the game, but in an online manner. And so this is a, a very interesting way of using distributionally robust optimization uh, to now navigate, very constrained and aggressive drivers that are in and around us. Uh, and this not only runs, in theory and on simulation, but runs for real in our evaluation platforms at 1/10 the scale, where we can just put in a new driver and analyze that driver's behavior on the fly and figure out how to overtake them with a high probability of success. A second theme is third theme is really on how do you actually design these vehicles, given that you have new EV platforms and new kind of use cases and constraints. How do you use previous designs to automatically synthesize uh, new designs for new use cases? And if you have a partial design that is hand done or from previous designs, how can you use, AI co-designers to auto-complete these designs? And so we are developing this tool chain that allows us to synthesize now uh, 80% complete or 100% complete automatically generated, designs by going through architectural exploration and doing parametric optimization, synthesizing detailed designs, evaluating it within our digital twin and OpenAI gym-based simulation system, and iteratively generating improved designs for the constraints. So if you're designing like a factory robot that has to do certain forklift maneuvers, this is a system that can use a previous design and synthesize something that is very efficient, but say on a different chassis and with a different sort of environmental constraints. We look at situational understanding and decision making in a safe manner by combining, formal methods with controls and dynamics. And this is with onboard verification, where in a receding horizon manner, we can actually, again, synthesize trajectories that are exhaustively safe as we go through this receding horizon, say every 100 meters or every 100 milliseconds. And this is by onboard verification to do that. Fifth theme is really on automatically now tuning for a given environment, tuning the vehicle planning and control software stack for different hardware. So how do we make sure what is the best optimized hardware and what is the optimized vehicle planning and software stack for this particular environment? And so for a different environment, how do you actually now tune this vehicle for a different racetrack, for example? So the whole point is that, you can swap out the hardware and swap out the environment, and we want to basically have this reusable core of autonomy components that can be parametrically tuned for matching the environment and the hardware. And so we've developed this automatic tool chain called tuner car, which automatically optimizes the physical parameters and for the planning and control aspects, and synthesizes the software code for that, and you can actually test it out for real on the 1/10 scale platform. And this has been very successful in doing that for the racing ODD, and now we would look at that for different use cases. You can see all the code is available here and demonstrations in the links below. So this is an illustration of how we can optimize for a given hardware system, where you can move the center of gravity, change the cornering stiffness, and optimize these parameters, optimize the planner and the control strategy for this particular path over here. And this is all done, in OpenAI Gym on AWS, and then you can see that it actually works on the real vehicle as we are running through. So this is the code generated and now running on the actual vehicle over here. So that vehicle is following that trajectory and that configuration as it was synthesized from the tuner car toolchain. We look at dynamic agent, multi-agent planning. That is, with you have when you have interactive agents, how do you now figure out, with different model predictive control strategies to adapt your driving capability with risk-based methods. So what are fast and reliable overtaking maneuvers? How do you effectively interact with other vehicles to figure out how cooperative or how adversarial they are? And then we also look at ethical considerations in those algorithms. All of this is captured, first through our simulation engines. We have, the F110's GIM that captures vehicle dynamics, that has very fast execution on AWS. And we can run, several simulations and hundreds of simulations in parallel. It's built for fast prototyping. And there have been several publications. There's just a few from the last year, and in ICML, ICRA, NeurIPS, and also on education in 6C. F110, really focuses on a collaborative partnership model where we do the research, we do hardcore research, but we're focused on not just on R&D, but R&D and D, where the last D is deployment. So it's research, development, and deployment. We're really focused on how do we get these to work on different hardware platforms. We also, F110 is also used in the Department of Transportation's Karma for collaborative and communicating vehicles. It's used for training the folks over there and for evaluating prototype software before they move to their fleet of 12 autonomous vehicles. We have also started a syndicated education program over the last 2 years where many universities now teach the F110 courses. We have developed 16-week courses and different types of long courses, short courses that go in depth into perception, planning, and control. And anyone can use that in our open syndicated education course platform that's on f110.org. And so essentially coming back to the point, this pitch over here is focused on OpenAV algorithm stacks for OpenEV platforms. And we are looking for a sponsorship for 2 years of funding between 225K to 350K. All the work that we do is in developing this ecosystem for OpenAV, for OpenEV. And so therefore it is open sourced. The deliverables to the companies are really a full stack, AV stack for these OpenEV platforms with a demonstration on specific use cases. And you can get more details on f110.org at this place. Thank you very much.